Okay, I think we can start. Thank you, everyone, for being here this afternoon. As you know, AIDA is presenting lectures with different topics on artificial intelligence. And today, we are really pleased to have a really interesting talk given by a really prominent researcher, Professor Manuel López-Ibáñez. Is professor at the University of Manchester in the Alliance Manchester Business School. And he's having a long curriculum on optimization and learning. He's editor-in-chief of an ACM journal on the transactions on optimization and learning, and also associated editor in others, ACM and IEEE journals, and he has a long-standing presence in both domains, optimization and learning, for about 20 years history. And we will have today the pleasure of listening from him about the automatic design of algorithms, which is really a hot topic, and whether LLMs can be part of it, and which part are good or not coming from them, and which other ideas that are existing out there in artificial intelligence for a long time. New ones that are different from LLMs can also be useful in the design of these techniques. So I hope you all will enjoy. Remember to keep tuned to AIDA lectures in the future. And today we are ready to start. So please, the floor is yours.
Thank you very much. Thank you, Enrique, for this kind invitation. You actually saved me the time for the half of one of my slides where I was going to introduce myself, and you had the kindness of doing that so I will skip this part. I just want to mention that my research is mostly about automatic configuration, selection, and design of algorithms. You might know, or maybe don't know, an automatic configuration tool called Iris. I will briefly mention it in the talk today. But I also work on empirical analysis of multi-objective optimization algorithms. I have published a couple of software packages for helping researchers and practitioners analyze their multi-objective optimization algorithms. I also work a lot on developing heuristics for combinatorial optimization problems, multi-objective or single objective, and I'm very much interested in human-in-the-loop aspects when a human is interacting with the optimization algorithm. So if you're interested in any of these topics, please don't hesitate to reach out. And I'm very interested in applications. So I collaborate with lots of companies in putting these ideas into practice. And I really like collaborations with companies because it's where interesting research questions arise. And a lot of the things I'm going to present here are actually motivated by talking with companies. So let me start with a claim that I believe is true, and maybe you disagree with it. I would like to hear from it, but I believe that modern high-performance optimization solvers involve a large number of design choices and hyperparameter settings. So if you know anything about exact solvers, like for example, IBM Cplex or Gurobi, or the open source solver Higgs, another open source solver is called Skip. All these solvers have lots of hyperparameters. This might represent different models, different preprocessing steps, heuristics for variable selection, value selection, branching rules in branch and bound, and lots of numerical parameters that can be tuned to make the solver perform better when solving particular problems. And if we talk about heuristics or meta-heuristic solvers, then we have different solution representations. Are you using permutations? Are you using binary encoding? Are you using a real value encoding, different operators? In the case of evolutionary algorithms, you have mutation, recombination operators. And if you have local search, you might have different neighborhoods. There might be different initialization strategies for creating initial solutions, and simply different strategies for performing the search. And of course, there are also many numerical parameters, and it's interesting that in many solvers, these numerical parameters are hidden in the source code. Somebody set the value to for example, 2.5 during some experiments, a bit of trial and error, and then this parameter value is hidden in the source code. But it doesn't mean the fact that it's set in the source code doesn't mean that it's a parameter. It's also a parameter that could be set to a different value. And this not only applies to optimization solvers, but also to machine learning frameworks. Maybe you know about the machine learning framework Weka. So this framework is immense. It has up to 700 hyperparameters that can be tuned to select different machine learning models and their hyperparameters of the machine learning models. There is also a framework that has been built on top of scikit-learn called AutoScikit-learn, and this framework has 100 hyperparameters. Software for AI planning, like LGP or Fast Onward, they have tens of hyperparameters that can be tuned. If we think about compilers that convert C or C++ code into executable code, these have hundreds of flags and parameters that can be tuned to make the performance of the compiler better, to generate better, more optimized code. Databases is also another example of software where you have lots of hyperparameters that can be tuned for different scenarios, different workloads, and in principle, we'll need a way to tune these hyperparameters. So basically, we have parameters, hyperparameters, however you want to call them, parameters everywhere that need to be set to a particular value. And when I talk about hyperparameters, parameters, I'm going to use the term parameter and hyperparameter the same because different communities use different terminology. For me, in this talk, it has the same meaning, and I not only mean numerical parameters that are more often found in the algorithms or when we are tuning, but I also mean higher level design parameters that are often categorical. So for example, your algorithm might have a local search, and there might be different types of local search that you can choose from, a tabu search, a simulated annealing. This is a hyperparameter that needs to be set. It might be a certain value design choice between using a neighborhood that is a small, medium, large. The precise value, the precise size of the neighborhood may depend on the input data, but you have these three choices, so you have an ordinal parameter. And of course, we have the classical numerical parameters that can be integer, it can be real value, but a particular characteristic of these parameter spaces is that you have very often conditional parameters. So some parameters that are only active for specific values of other parameters. For example, we might have a framework where we have a numerical parameter called temperature, and this parameter only makes sense, is only enabled if another parameter called local search takes a particular value. In this example, simulated annealing. And when we are configuring an algorithm, we need to set the value of all these parameters, the categorical, the ordinal, and the numerical ones. So how this is done traditionally? Very often, still nowadays, this is done by human expertise, intuition, trial and error, maybe some statistics, a bit of design of experiments. But the idea is that you have some benchmark problems, or if you're doing machine learning, some training data, and you have your knowledge about the literature. You might have a framework where you can instantiate code, you can write code and set the parameters, and you use these benchmark problems to basically decide the design and the hyperparameter values of the solver. And then you put it in the real world, and you hope that in the real world problem instances, the solver will work well. This is not easy. Maybe you know the person in the screen, Donald Knuth. He's the author of The Art of Computer Programming, a very well-known book. And Donald Knuth himself says that parameter optimization is a daunting task. And this is not only because differences, in his case, he was solving satisfiability, so he's talking about the satisfiability problem instances, but this is a comment that applies in general to having different problem instances or different training, different data sets that you want to obtain good performance on those data sets, but also because the algorithms themselves often have some stochastic components, they do some random choices, and it's actually difficult to know when changing a hyperparameter value will be beneficial or harmful without actually trying, so without actually performing the evaluation. And we have a situation where these traditional approaches guided by expertise and intuition have many issues. One is that they are prone to overgeneralization, so we run some experiments, maybe we do some statistics, but we don't really explore the parameter or the design space, and we make quick conclusions, and we overgeneralize these conclusions to different data sets to which they might not apply. There is also little exploration of design alternatives because we might only explore the things that we know, the things that we are experienced on. We might make some assumptions about the interaction between the parameters. And then there are human biases. For example, if we are tuning two different approaches, two different algorithms, and one of them was invented by us and the other is the competition that we are trying to beat, maybe even unconsciously we spend more effort tuning our own algorithm than tuning the competition. And yes, there are theoretical studies sometimes that can guide the hyperparameter values, but these theoretical studies are often based on oversimplifications, and when we go to real-world problems, they might not apply. They might have some specific assumptions that, again, the real-world problems or the real-world algorithms don't satisfy these assumptions. And when everything works, the theoretical studies often only refer to one or two parameters and don't consider the interactions with other parameters. And we have seen that modern software have tens, hundreds of parameters, and so they don't apply the theoretical studies. So how can we make this approach more principled, but also how can we make it less human intensive, more automatic? And the traditional approach is called the algorithm configuration problem. So the idea is that we want to find the best algorithm configuration given a set of training problem instances, or in the case of machine learning, given a set of data sets that we want to generalize over. So we want to then, after we find this algorithm configuration, we want to repeatedly use this configuration to solve unseen problem instances that hopefully come from the same distribution, or unseen data sets that hopefully come from the same distribution. And this is a problem with many names. The optimization is classically called the offline parameter tuning or automatic algorithm configuration, which is the term that I tend to use. In machine learning, it's called hyperparameter optimization. There are also approaches within the field of hyperheuristic and genetic programming that try to solve this problem. In the 80s, in the 90s, it was called meta optimization because you were using optimization to optimize the optimizer. And some years ago, somebody proposed calling it programming by optimization as a more general framework of how to guide the generation of code with optimization. And how this problem can be solved? Well, this automatic algorithm configuration or hyperparameter optimization is basically a mixed integer stochastic black box optimization problem. It's mixed integer because you have categorical, ordinal, and numerical parameters, numerical variables. It's also stochastic because the algorithms that we are tuning, the algorithms that we are configuring are often stochastic. And even if the algorithms themselves are deterministic, we are using training data, we are using training problem instances that are but a sample from a larger space. So we have the stochasticity that arises from trying to create a configuration, trying to find a configuration that is robust to unseen instances from a larger space. Also, it's black box because we don't have a mathematical description of how the parameters interact with the algorithm and the problem and the data. So the only way we can actually know whether a configuration works or doesn't work is to evaluate it, is to set the parameters of the algorithm to particular values and run them on one or more problem instances. And then we get a measure of the performance. And this might seem a complicated problem, but actually there are many methods in the literature to tackle this automatic algorithm configuration. One of the most popular have become Optuna, which is widely used in optimization and machine learning. Also, another very popular method is called SMAC, And it was one of the earliest methods proposed, and it had a lot of impact in the community. And I also have proposed a method that is mostly used in combinatorial optimization, which is called iRace. And there are many more. You can find many hyperparameter optimizers. Some of them seem to be abandoned, but there are many more in the literature. All of them work basically in the same way. You define a set of training instances. This, if you are doing machine learning, this will be different data sets that you can use for training. And then you define a hyperparameter space or a parameter space, which defines how many parameters you have, their types, the domains, any conditions, any constraints between parameters. And then you have a performance metric that will tell you when a configuration of the algorithm is considered to be good or not. And then you have the input target algorithm and the algorithm configuration. What all algorithm configurators do is to sample configurations from the parameter space, run the algorithm with that configuration on a number of instances, because we are trying to overgeneralize. We are trying to generalize over the set of instances. So we are not so interested on being good on the training instances, but trying to be good on instances that might come from a similar distribution, but we have not seen yet. And then we get performance values for running the algorithm on the various instances, and the configurators aggregate these performance values in some way to try to identify a best configuration. So with this introduction to algorithm configuration, hyperparameter optimization, you might now have changed your view, and you might see an algorithm instead of a monolithic, having a monolithic view of an algorithm, more like a box with many buttons and dials that you can play with, and you can use configurators to set the value of these buttons and these dials. But actually the view that I want to promote is more like a puzzle. It's more components, different components that can be fit together to create an algorithm. And yes, I don't have a picture of this, but the blocks of the puzzle might have buttons, might have dials that need to be tuned, but you also need to decide how the pieces of the puzzle are put together. And the idea of this approach is that we will have a set of algorithmic components. How these algorithm components are created, I will explain later, but also we will have rules for combining these components. With this combination of components and rules, we can always create a parameter space that describes this design space. And if we have a parameter space, and this parameter space may be quite complicated because it needs to embed all the rules and all the possible algorithmic components, it may be hundreds or even thousands of parameters, but we know we have very good automatic parameter configuration tools. So given this parameter space and training instances or training data sets, we can use one of these tools like iRace, like Optuna, to create effective algorithms. And there are basically two approaches to how to do that. One approach is called the top-down approach. So we create what can be seen as a monster algorithm or a meta algorithm that is basically an algorithm template that has template parameters where you can fit the different components, but the structure of the template is fixed, basically. And this is something that we see, for example, in mixed integer programming solvers. They can be seen as a top-down approach because basically they contain lots of possible components. Most of them are disabled by default, but you can enable them if you set the proper parameter to the proper values to various parameters. A very famous example of this approach, of the top-down approach, was the Sattenstein framework, which was a framework for satisfiability that won several competitions. And we have also proposed a framework, a top-down approach for designing multi-objective evolutionary algorithms, and now several multi-objective evolutionary algorithm frameworks for Python and Java have adopted as a way to automatically generate automatically design such algorithms for particular applications. But perhaps more popular, it has been more widely adopted in machine learning. For example, the AutoWeka framework just used Weka as the to create a fixed template so you can instantiate machine learning components from Weka automatically. And the same was done for scikit-learn. So there is auto scikit-learn, which allows you to basically use optimization, use automatic configuration tools to instantiate machine learning, complicated machine learning pipelines from scikit-learn automatically. The downside of the top-down approach is that you have this fixed algorithm template. So a human has to sit down, define this template, and then it becomes very complicated to change the template. It has a very fixed structure. So a different approach is called the bottom-up approach. And here in the bottom-up approach, what you have is a library of algorithm components, and then some rules that tell you how to compose the algorithms from these components. This is often done via grammars. So you have a grammar description, a generative grammar that tells you what instantiations of these components are allowed. And there are many examples in optimization of these bottom-up approaches. Some of them use genetic programming, some of them use grammatical evolution. There have been also proposals using arrays. I will talk a little bit more about them later. And in machine learning, they are also they have also been proposed. There is, for example, the framework TPOP or the framework RECIP, which was for creating classification pipelines in machine learning. So let's see in more detail an example of bottom-up approach. So some time ago, we proposed a bottom-up approach to design stochastic local search algorithms. So local search algorithms, single-point local search algorithms, just take one solution to an optimization problem and try to do small changes to try to improve it. This is very useful for combinatorial optimization, but for example, if you know stochastic gradient descent, it can be seen as a stochastic local search method as well for numerical optimization. And the idea is that there are many proposals in the literature for how to design this stochastic local search method. So we wanted to be able to automatically design hybrid local search methods. So the steps that we did is we decomposed these methods from the literature into algorithmic components, and then we devised a generalized meta heuristic, a generalized meta level. But instead of creating a fixed template, like we will do in a top-down approach, what we create is a grammar that describes how these meta algorithms can be generated. And then we can convert this grammar to a parametric representation, and you can find the details in the papers, which has the benefit of having a parametric representation that we can use off-the-shelf automatic configuration tools. In our papers, we use arrays, but we could have used Optuna, SMAC, or any of the other tools available. So just to give you a flavor of how this works, this is the description of this generalized local search. Is a very simple algorithm. It has an initialization that creates an initial solution to a problem, and then it calls a main procedure with this initial solution that has 1, 2, 3, 4 components: a perturbation, a local search, an acceptance, and a stop criteria. And this will return a solution, and this is the solution found by the algorithm. Inside this function GLS, what we have is a very simple loop. There is a local search applied to this initial solution that creates a new solution, and then we loop while the stop criteria doesn't tell us to stop. We perturb the solution created by the local search, we create another solution, and then apply a possibly different local search, and then we have an acceptance criteria that has to choose between the last generated solution or the one generated by the previous iteration of the loop. When the loop stops, we return what we found. The key here is that this local search component in this GLS algorithm can be a different GLS. So it could be another instantiation of this GLS function. And this means that we can generate many stochastic local search methods from the literature following this very simple template. So some examples from the literature is we can reproduce simulated annealing by setting perturbation and local search and acceptance as you see in the screen. But there are many other algorithms from the literature: variable neighborhood search, iterated greedy, taboo search. There are many algorithms proposed in the literature that can be generated from this GLS framework. But also we can generate many algorithms that have never been proposed in the literature because we can hybridize it and we can choose these components in a completely different way. To give you an idea how this grammar works and how complex or simple, depending on your point of view, is, you can see a snippet of the actual grammar. Basically, we have the main algorithm here that I explained before, but now it's in grammar form. We have the initialization, we have the call to the GLS, and then we have the return of the best solution found by the GLS. This GLS could be one of the known meta-heuristics that I have described before, so iterated local search, simulated annealing, iterated greedy, or it could be a hybrid. If it's a hybrid, then we have a call to GLS, and the local search in the GLS is another GLS that will go again to this rule that will need to be expanded again. Of course, there are many more components. We need to expand the perturbation, the local search, the set time. All these components are defined in the grammar. Some of them might be problem specific. Some of them are problem independent. So one can create a huge variety of algorithms from this small snippet of grammar. So how do we actually generate algorithms? So basically we have a problem-independent grammar, a problem-specific grammar, and then we have a piece of software that we wrote that can transform these grammars into a parameter space description. And then we have iRace or any automatic configuration tool, any hyperparameter optimization tool that can use this parameter space description to sample parameter configurations. Each parameter configuration actually represents an algorithm. And from this parameter configuration, we can do the reverse decoding that reads the grammar again, and we decode the configuration into source code that is compiled and executed and evaluated on one or more problem instances or data sets. And this is a cycle. We run this cycle for this loop for many, many iterations, possibly evaluating thousands of algorithmic designs. And after a while, we stop and we have a very good algorithm for the problem instances that we give as training instances. This framework originally was a new idea that we saw very promising, but of course, when you put things in practice, you start realizing that some things are not so easy as you thought. So for example, one of the things that we found is this compilation step is very slow. It slows down the whole process, and also is very error prone, because if you make a mistake in the grammar or in the components, you might not detect the mistake until iRace or the configuration tool instantiate that part of the grammar and compile it. And debugging becomes very, very bothersome. So Pagnosin astutely, a few years later, redesigned the framework. And in the redesign, they have a single executable that is already compiled and optimized, but this is an executable that can understand the grammar, can understand a sequence of instantiations from the grammar, and automatically builds in memory, without need for compilation, builds in memory the algorithm that is going to be executed, which saves a lot of time and makes the system much more easier to develop and evaluate and debug. And actually, in their paper, they showed that they can achieve years of progress in combinatorial optimization by proposing new state-of-the-art algorithms for several combinatorial optimization problems that have been studied in the literature, and humans have proposed state-of-the-art algorithms, and they were able to surpass the state-of-the-art for several problems in just a week of computation time. But there is also another difficulty, is that somebody has to write this grammar. As I show in the previous slide, the grammar, yeah, it's readable, but it's not so easy to write and to maintain. Especially, it's not so easy to modify if it becomes very large. So more recently, we have proposed what we call automorph, and the idea is that we have a hierarchy of components. The hierarchy of components actually encodes the relationships between the components, but also we have additional annotations in the code that tell us if a component is deterministic, a component is stochastic, what features or what properties, what functionality the component can achieve. So can it be used as an initialization? Can it be used as an acceptance criteria? And what other components are compatible with it? And using these annotations and hierarchy of components, we don't need the grammar. We can dynamically, implicitly generate this grammar. So we have proposed a redesign of the previous system where we have our sources that are annotated, and we have a scanner that scans the sources, generates implicitly a grammar that is immediately converted into a parameter space. And now that we have a parameter space, well, you know the story now. We can use automatic configuration tools like SMAC, Optuna, iRace to basically search the parameter space. But we also have a system that analyzes the results and is able to provide additional feedback to the configurator. And in this way, we can simplify the whole system because we don't need a grammar. We don't need a grammar. And we don't have the issues of maintaining a grammar, especially. It becomes very, very easy in this approach to add new components because you only need to annotate your component that you're adding. You don't need to touch the rest of the system. And this allows us to generate new state-of-the-art algorithms for different problems. We actually tackled 3 different problems in the paper. And you see 2 examples of algorithms generated from this system. They are not exactly, they are similar to algorithms that a human would generate, but a bit more fine-tuned, a bit more specific. They have some complexity that maybe a human would not have thought about. But they are still recognizable. They are algorithms that a human will recognize if you have some expertise on local search for combinatorial optimization. Yeah, here I show the results, but I think it's probably more interesting to talk about where do we go from here. And one of the things that you can do when you have such a system is that you can actually analyze the components while you are doing the whole automatic design and try to understand the complexity of the various components. In the simplest way, in the empirical complexity analysis, you could run the algorithms and try to fit a model to the runtime of algorithms depending on the input size, on the size of the input. But since you have the framework and the components know the relationship and how they call each other, you can do something more reflective, which is you can understand exactly how much effort, how much time was spent on each component, how many times one component called another component, so one component was a child of another component, and then you can use this information to build more precise models, to build models that actually know how many times a component has been called, how much time has been spent executing that component, and actually how much performance, how much improvement the component has done. And this is still work in progress, but this shows that it's not only about obtaining the best possible algorithm, but also the whole process generates a lot of data that can be analyzed to try to identify possible improvements of the system. But you might be wondering, okay, but how does this work in the age of LLMs? What can we do? Will not LLMs get rid of all the system? Do we need to do any parameter tuning if the LLM can tell me what are the best parameter values? So basically, LLMs are being used in optimization and machine learning for 2 different things. In optimization, there is a trend where people specify a problem in natural language and the LLM is able to generate a mathematical model. But then an actual optimizer written by humans is used to solve the mathematical model. And this has worked very well for things like constraint programming, which is a type of mathematical model that are very powerful solvers for solving constraint programming problems. But they still require very carefully crafted prompts that contain a lot of domain-specific expertise. The other approach is the one that was developed by or proposed by Google DeepMind in a paper, I think it was in Science or Nature, and it's called FunSearch. and then has been improved by other researchers. One of the most famous improvements is evolution of heuristics. The idea here is to ask the LLM to automatically design heuristics, to actually create the code for the solver. The downside of that is that the examples in the literature, for example, the example of fan search, the problems that they are solving are relatively simple. In the fan search paper, they tackle the one-dimensional bin packing. This is a problem that has been studied for 50, 60 years. There are very well-known heuristics for this problem. There is a lot of literature, and actually the competitors that they consider in the paper, they are the simplest heuristics that you can think about for bin packing. So it was not that surprising that fan search was able to generate better heuristics than for the one-dimensional bin packing. So in recent research, we have been studying what is the actual potential for solving more realistic problems. And we consider a far more realistic problem that is the 3D container loading. You can understand it as a 3D bin packing. In particular, we have studied so far what is called the single stock size cutting stock problem. It's a very complicated name, but what it means is simply that you have containers that are of the same size, and you have boxes that are cuboids that you can rotate. You don't have any restrictions on how to place them. They can just not overlap. And the other restriction is they cannot stick out of the container. They have to be contained inside the container. And the idea is that you are given a lot of boxes of different sizes, and you have to optimize the packing to use the fewest number of containers possible. So we asked the LLM, please implement a function that selects an item, an orientation, which container to put the item, and the position within the container. And if we apply the classical evolution of heuristics approach, this fails catastrophically. If we ask the LLM to generate 20 different heuristics, 16 of them will just not compile. The heuristics will not run because of errors in the code. So the LLM is generating Python code because we didn't care about high performance code here, and Python LLMs tend to be better at generating Python code. So it simply cannot generate correct code. So we did two improvements to AOH. One improvement is that we provided what we call a constraint scaffolding, which is basically we give the functions already written by us that allow the LLM to check that the constraints are correct. In this case, to check that the items are inside the container and that the items don't overlap with each other. And if we do that, we actually reduce the code errors significantly, but we don't completely eliminate them. We still have 4 out of 20 runs result in a code error. So we also added what we call iterative self-correction, which is basically very simple. We take the output of the Python interpreter and the code generated by the LLM, and we feed it back to the LLM and asking the LLM to correct the code to remove the errors. And if we repeat this 3 times, we end up without any errors at all, but still sometimes the code generated runs for too long. Sometimes it might be trapped in an infinite loop, or it's doing operations that are way too expensive. So it doesn't complete successfully. But in 17 out of 20 times, it's able to generate a heuristic. So how good is this heuristic? If we compare against human design algorithms, and here we are trying to minimize the number of containers, here at the bottom of the table, you have the results of the LLMs, and you can see that they are better than the most trivial LLMs like the most trivial heuristic like first fit, but they are not so close to the state of the art in the literature, to the human design state of the art. So this was a bit disappointing, but one thing that we had an idea is, okay, maybe it's just too difficult to beat the state of the art, but is the LLM at least generating something new, something that has not seen before? And how can we use this novelty in a productive way? So what we thought is an approach that takes the scoring function generated by the LLM and use it to generate many different possible packing patterns. So this is different ways to pack the boxes, which might not be optimal, but they provide multiple alternatives. And then we use an algorithm that solves what is called a set partitioning problem to find the best combination of patterns. So we are not actually optimizing the placement of the boxes. We are simply choosing between different patterns that can together pack all the boxes. And this actually proves to be much, much better, the result. In fact, we are very close to the state of the art with this approach, and we can beat some of the algorithms published in the literature that were also close to the state of the art. So it was much more productive. So in summary, for talking about LLMs for automatic algorithm design, the things are, for example, don't get better if we add more real-world constraints. If we actually add constraints like, for example, that big boxes cannot be placed on top of small boxes because of stability, or there is some fragility constraints in which some boxes can only support a certain height, otherwise they will break, then the LLMs generate even worse results. So I will say that, according to my opinion, we are still a bit far away from AIs independently solving non-trivial problems, but if we guided by human expertise, we can use the LLMs to generate components, and then we can use other techniques like the ones that I have discussed before, hyperparameter optimization, bottom-up approaches, to actually find out how to recombine these components, how to use these components in different parts of an algorithm, of a complex algorithm. So between the two sides of don't believe the hype and the hype is real, I was very close to don't believe the hype. LLMs are not going to solve any problem. Now I'm 50-50, let's say, maybe 40-60. I'm starting to be a believer, but not there yet. I think we need a lot more research and development on using LLMs to replace everything else. So some few conclusions to take home. If you have never used automatic algorithm configuration or hyperparameter optimization, use it, because this is a standard technique now. There are very good general purpose tools, and it's a very, very mature technology nowadays. But thinking more forward, we are going to see a move, we are already seeing a move from monolithic algorithms to flexible frameworks of algorithm components. And this is a paradigm shift in optimization and machine learning. And these frameworks of algorithm components are going to be used in a different way, where a human is devising novel algorithm components, and we have a CPU-intensive automatic design phase where we generate many possible designs, and then we have an analysis of this generated data, for example, the empirical complexity analysis I have described. And this analysis could help humans to design new components to add to the framework. Of course, the situation is slightly changing because now we not only have humans involved in this loop, but we have LLMs that can devise novel algorithm components and LLMs that can analyze the generated data and drive improvements to the components. So quit living in the past, because the future is here today. And if you have any questions, I will be happy to answer them.
Thank you, Manuel. Thanks a lot for the presentation. Any questions? Please go and do it. The first one I would like to do is, well, at least two of them. One is, what about using few shots or not? How much is few shots helping to train LLMs or to use them for this? So few shots is one thing, not just telling them and instructing them. So using a grammar example, but a few shots clearly what we want. And second is, how much is this dependently of the set of problems? Can we do an approach, even if we are going for components approach that is just for one problem, or could it be done going for components but for more than one problem?
So one of the things is that we, in the experiments that we have been doing, and other researchers have found the same, the LLMs are particularly bad at tuning parameters, especially numerical parameters. They tend to overfit, or they tend to set nonsense values that don't make any sense. So I think that we have to devise more general approaches that are going to combine components that have been tuned by external tools, so more an agentic LLM that actually uses a framework that is already built with annotations in the source code, maybe even with comments aimed for the LLM. And the LLM is actually serving more as an agent than just as a code generator. So the strategies that have been used originally proposed use the LLM as a way to generate code, but this is not proving to work that well for generating high performance algorithms. And actually what works better seems to be to use the LLM as an agent that is calling a framework, a general framework, or calling general solvers, general hyperparameter optimizers, and then analyzing the output. I don't know if this answers your question completely.
Yes, indeed. Thank you. Any questions? There is a question, Manuel, also in the chat about annotated sources.
Yeah, so the annotated sources is a very general term. You have annotations in Python, but also in Java. It could be just comments in the source code. So it's basically that instead of you sitting down and thinking, okay, this algorithm component, where does it fit in my algorithm design space? What you think is, okay, this is a component that it requires is a stochastic. So I'm going to annotate it saying that it's a stochastic. If you call it multiple times, it produces a different output. It's a component that requires as input a solution that is fully completed or a partial solution, or is a component that will take n square, n cubic, or takes a random, or takes the output of other components. So basically, these are properties that are particular of the component. And when you analyze these properties, or when the system that we propose analyzes the properties, it can find where it fits in the algorithm design space. In the machine learning, you could see it as, for example, is this component a preprocessing step, a classifier, a regression method? Is it component for linear? Is a linear model? Or is a non-linear model? So characteristics, meta features, you can call them, of the component that could help the system to identify where it can be used. So you avoid creating algorithms by combining components and putting them arbitrarily anywhere that are invalid, that are doing some nonsense, like putting a preprocessing step at the end of the pipeline, for example. That will make no sense. So this is the purpose of the annotated sources. How it's implemented, it depends on the programming language, or it might be just based on comments, structured comments in the source code. Does this answer the question?
It seems very thorough. Yeah. I would have maybe a next question. Given the speed at which we are evolving with the use of LLMs, in which every month, at least, we are having interesting advances, let's say. How much time do you think we will have from now until LLMs are actually moving you from the 46% till the 90% believer in not just going for the components, but also in playing with the components and actually having a design that is mostly automatic?
So I think there is, this is my experience, and from reading the literature, maybe there is some other papers that I haven't not read, but from my experience, there is a lot of hype, but also there is some reason for the hype. And what I mean by this is that, for example, one thing that we have realized is that, as I mentioned before, the LLMs are not going to tune your algorithms. They are just very bad and very inefficient and tuning hyperparameters. But the LLM can call an external tool to do it. So we are not going to have in the near term, at least is what I believe at this point with what I know, we're not going to have an LLM that you can just describe a very complicated problem for example, a 3D container loading problem with some reasonable constraints, and the LLM will generate automatically an algorithm that can solve the problem to the level of a human expert. However, what we are going to have is a framework where you have some parts and the LLM can suggest improvements. Like, for example, it can suggest a new initialization, how to create a new initial solution that maybe the initial solution is not better quality, but it's so different from what a human would have done that actually helps you to create more diverse solutions to obtain solutions that you might have never seen before, or create a new neighborhood operator, or it could actually just guide you with some iterations, some optimization added on top to think about possibilities that you have never thought before, but they are somewhere in the literature. So it's not something that I see immediately replacing humans, despite all of the news that we see that LLMs are continuously improving. What we see is that many of the improvements are based on actually smarter ways to tell the LLM what it needs to do, and smarter ways of the LLM making use of the things that are already available. So having a more clear framework that the LLM can easily interact with, having external tools that can interact with the LLM in a more efficient way, the data transfer is clearer. So for example, one of the recent improvements that we have done is that to let the LLM actually understand the syntax tree of the program and try to identify when it's generating code that is too complicated, that is bloated because it has too many parameters, and these parameters will need tuning. Maybe they don't have a positive effect, and actually just it will generate more bloat. So how to simplify the code that the LLM is generated? We just provide more information to the LLM to reflect how to do this. But this needs a human to actually think about how to communicate this information, how the LLM could make use of this information. So I don't think that LLM is going to replace these tools in the near future.
Okay, thank you for that. I don't see any more questions.
There is somebody has raised their hand. Itamar? Oh, okay.
Yes.
Okay.
I'm very impressed by this fantastic talk and survey of different methods. I have wondering about, at some point you use the grammar and then you say we can ignore the grammar and go on. And that's very interesting and intriguing in the sense that maybe by exploring this further, I can find out what's the real role of the grammar and also understand even better the LLM.
Mm-hmm. Yeah, I mean, we have not tried to see how the LLM understands the grammar, but one thing that is true in other fields, not in optimization machine learning, but we should learn from all these other fields, is that other fields, for example, chemistry, that when they are using LLMs, they have redefined the language. The LLM is not working on natural language, but it's working on molecular language. So they have they have redefined the talking space so that the LLM will be talking a language that is more appropriate for the task at hand. And maybe what we can do is to try to teach LLMs to talk in optimization or machine learning language. Because actually, we know that if we provide a pseudocode, the LLM is going to be able to generate the code in Python, in R, in C++. That's not the difficult part. The LLMs are very good at that. What is difficult is to search this grammar space implicitly or explicitly. But this grammar space sometimes is, as you saw in the results that I show, the LLMs seem to be struggling with it because we are exploring this space in Python right now. The LLMs are working on natural language and on Python language. And why add these complications? Why not let the LLM work on a higher level language that is talking about solutions, neighborhood, perturbations, or classifiers, regression models. There is pre-processing steps. There is a token space that is higher level, but maybe this can make the search of this, the implicit search of this grammar more efficient. And it's something that we have not seen.
So we may think that the LLM, if we make it subject specific, it will bring better understanding and better results.
Possibly. I don't know. This is an open question right now. Then I don't. Maybe somebody's working on this question right at this moment.
I hope somebody will find a thesis about that.
Me too.
Thank
If you know any work, please send it to me. I'm very interested in this topic.
Thank you very much.
Okay, wonderful. We have one more question in the chat about automorph and how the operators would know about the restriction and the representation used.
So this was one of the examples I should have given. So that's a very good question, and it's one of the things that the annotations in the source code actually help with. So one of the possible annotations is this operator works with a binary representation, or is only applicable to numerical decision variables in the problem, or if it was machine learning, this machine learning model only works for categorical data, so you need for numerical data, so you need a preprocessing step before to make it compatible with in the pipeline with data that is not numerical. So these are the things that you can encode in the annotations, and you write these properties, these meta features at the local level in the component, but then the scanner scans all these properties and can reason how this component, the properties of this component, allow to fit the component or use it or not use it for a specific problem. So if you have a problem that is permutation based, all components that don't support a permutation representation will not be selected, will not be part of the implicit grammar. And this is the powerful thing about the annotations, that we don't have to rebuild the grammar every time we change problem. We don't have to figure out where the component fits, but this comes for free by just annotating the components. Okay?
Okay. Yeah, there is no more question. I think that we are solving very well all questions in the chat, and also ourselves here talking. So thanks a lot for that. I think we are ending the presentation. I would like really to thank you, Manuel, for this wonderful
Thank you very
presentation.
much for the invitation.
Thanks a lot. I would say to all attendees, please keep tuned to the AIDA lectures, because they are really interesting for artificial intelligence in general. And I see you in the next presentation. And thanks. And that's all for today. Bye-bye.
Thank you very much. Bye-bye.